Can you hear me in the chat? Wonderful, thank you. Okay, so as usual, don't forget the seating survey, section 4. Upcoming deadlines are this Friday, we have homework 9. Sunday is the Piazza participation cutoff for week 10. And Tuesday of next week is possibly the guided inquiry small group activity 4 deadline. So a couple things about the small group activity. The first is that most of the groups have changed at least somewhat. So check to see who your group is now. The reasons they have changed are many. Sometimes somebody has dropped the class and so you need somebody else in the group. Sometimes there were reports of students being extremely frustrated by group members that are only showing up in the last hour or two before the assignment is due. And so I'm trying to combine people into groups that have the same sort of work style. So make certain you are looking at who your new groups are. Everyone should be in only one group, and every group should have 3 or 4 people in it. If either of those two things are incorrect, then let me know. I made a mistake somewhere and I will fix it. The second thing, on the deadline for it, there was a request that came into me on Piazza about pushing it back a day or two. I'm nervous about doing that because that'll push it closer to when the Newton assignment is due, but I am willing to consider doing that. And so I put a poll up on Piazza to try to gauge the preferences of the class. So take a look at that if you care when it's going to be due. Do we have any logistical questions before we get started onto content? This particular group activity should be the shortest of the bunch that you've seen so far. And in some ways, one of the more straightforward ones. It's essentially just dealing with buffer systems that are present in the bloodstream. And so the amount of having to extend yourself to understand what's going on in it should be lower than what you've seen in some of the other activities that we've done. Okay, let us start going through some content. So there was one question on Piazza about the difference between an ion product constant and the autoionization factor. So an ion product constant is the name for an equilibrium constant that results from only product ions being part of the equilibrium. So for example, you could have, the example that's frequently used is 2H2O is in equilibrium with H3O plus OH minus. The equilibrium constant for this would just be the concentration of hydronium times the concentration of hydroxide. But you could also have an ion product constant for something like the dissolution of sodium chloride into water, where you're making Na plus Cl minus. And so the concentration of the sodium and the concentration of the chloride are the only concentrations that matter. They are both ions, and so this is an ion product constant as well. In particular, it is called the solubility product in this case because we are looking at the dissolution, but that is a type of ion product constant. Autoionization factor is the same kind of thing for any case where you have something on the left that is that then makes two things on the right that are ionic, but the things on the left are the same. So water is an example of that. You could imagine something similar with two NH3s being in equilibrium with an NH2 minus and an NH4 plus. So this could be an autoionization factor as well. So auto here meaning self. It is something that is ionizing itself that's going on this way, rather than having things that are already starting out ionic, like the sodium chloride, and they're simply getting separated in the dissolution. So the equilibrium constant for this particular reaction here can be described as either an ion product constant or as an autoionization factor. But the two do have slightly different meanings. However, those meanings are not meanings that I'm going to be emphasizing very strongly. I am simply bringing it up because some people seemed to have gotten confused about about these terms being used either in Newton or on the textbook. Any questions on that aspect? Okay, so let's talk now about some calculation stuff. So the first general question is, when do you use ICE tables? So the general answer to when you use ICE tables is anytime you have initial conditions and you are allowing it to approach equilibrium, and you're wanting to find out the characteristics of the equilibrium sample that you have. There are occasionally shortcuts that you can use. The Henderson-Hasselbalch equation is one example of that, which can be a quicker way to do the same thing an ICE table does in some situations. And we will go into examples of that later in today's class. But if you are dealing with an equilibrium situation where you are given initial conditions that are expected to shift, and you want a quantitative piece of information rather than the qualitative idea of which direction does it shift, pretty much an ICE table will get you there. It's just that there may be some other cases where you can get there a little faster with some of the shortcuts you're about to see. Okay. How do you know when we can neglect things in the ICE tables? So there are really two places we have seen neglecting something in an ICE table. So for example, if we have an acid reaction, like so, so sometimes we will have some concentration here, say 0.1, maybe we're starting at 0 here. And sometimes we will neglect the amount of hydronium that we already start with in this case. So strictly, it's going to be 10 to the minus 7 that we have here. But not necessarily will it always be that. Sometimes when we have a change that we have down here, we will say 0.1 minus x, x and x, and sometimes we will neglect x down here. So here we have a decision to make. Do we neglect the initial concentration of the H3O plus? Oops. And here we have the question, do we neglect X? And the answer to that in both cases is we have to check. And so if we are doing a calculation here and we find that whatever X is small compared to 10 to the minus 7, then we needed to take into account the 10 to the minus 7 that we had here. But if X is large compared to 10 to the minus 7, then we can ignore the 10 to the minus 7 that's here. In this case, can we neglect the X? Well, we're comparing it to the 0.1. And so if X is small compared to the 0.1, we can neglect it. If it's not, then we have to include it. So what we are going to find in a lot of acid-base cases, particularly when we are dealing with a buffered system, if we're in the buffer regime and if we go ahead and pre-shift the equilibrium one way or the other in those situations, then we usually are able to ignore X. But it is absolutely something you need to come back and check to make sure that's the case. We'll go through an example of that when we look at some buffer calculations using an ICE table, and we'll do the same buffer calculations using the Henderson-Hasselbalch equation and see what the connection is between them when we get down there. Any questions on that general idea of when we can ignore the components, the various values here? It's all about compare it to the thing it's being added to or subtracted from. And if it's small compared to it, we can ignore it. Question on the chat. What if your HA is a solid? So yes, this is right. If your acid is a solid, you don't include it in the equilibrium expression. So you would get rid of it on this side. Okay. What is the equation we use to find the final answer after making an ICE table? So I suspect that this is coming from people going through a particular calculation or watching an example of a particular calculation, and then seemingly magically down at the bottom, there is an expression that includes some of these things from the ICE table, and people are trying to figure out where that's coming from. So the thing to remember here is that this E line stands for equilibrium. And so what we use there is the equilibrium constant expression for whatever the reaction is up here. In this case, assuming that we're not dealing with the solid there, we have aqueous systems here. Our Ka is concentration of A minus at equilibrium, concentration of H3O plus at equilibrium over the concentration of HA at equilibrium. Well, at equilibrium, these are the values that we have, and so those things get plugged in to these positions in order to solve the equation. So this equation that we end up using at the end of the ICE table is just the equilibrium constant expression for the equilibrium we are dealing with. Okay. There was some confusion as well about units. In particular, an example case where you end up with something like molarity to the fifth or something like that. So what's going on here is that when you make an equilibrium constant, you have the concentrations raised to the powers of the stoichiometric coefficients. And so if you have something like A plus 2B is in equilibrium with 5C plus 3D, something like this, and if all of these are in solution, then our equilibrium constant is going to be concentration of C to the fifth, concentration of D to the third, over the concentration of A to the first, concentration of B squared. And each concentration, remember, is in units of molarity. So in the numerator, we have molarity to the eighth. In the denominator, we have molarity to the third. So the overall units are going to be molarity to the fifth, because three of them are going to end up canceling as we go through this. So equilibrium constants can have all sorts of different units based upon the stoichiometry of the reaction you're dealing with. Question from the chat. That assumes the reaction is an elementary, right? No, it does not, in fact. If this were a kinetics problem, then yes, we would only be able to write this expression for elementary reactions, reactions that we know are single steps. But we went through an analysis when we first introduced the idea of equilibrium constants that shows that if you have a multi-step equilibrium, that means that all of the steps are equilibria that are part of it. And then all of the intermediate components cancel out when you come up with the overall equilibrium constant, so that this kind of expression is true, even if this is there's a multi-step process that goes on here, and there are in fact intermediates that are involved. So in this sense, equilibrium constants are easier than kinetics, simply because you don't have to worry about whether you're dealing with a single step or a multi-step process. Okay. There was also a question about what you do in the case where you have an equilibrium and then there might be a limiting reagent of some sort. Well, so normally when we think of a limiting reagent, we are thinking of a reaction going to completion. So if we have A plus 2B goes to C, then, and if we start with 1 mole of this and 1 mole of this, then we're going to run out of the 2B first, leaving behind 0.5 moles of A, and we're going to end up with 0.5 moles of C, but none of the B, because that was the limiting reagent that got used up. When you're dealing with an equilibrium, however, then you're never going to the point where any concentration has fully gone to zero, certainly not at equilibrium. Maybe in a shifted initial conditions, you might do that, but you don't do that in at the equilibrium itself, because if you have a product that has a zero concentration, then you have a zero in the numerator and the equilibrium constant is zero. Or you have a zero in the denominator if the reactant is the thing you run out of, in which case the equilibrium constant is infinity, which is not really a meaningful thing either in the context of an equilibrium. So the only place where we really bring in the idea of of limiting reagents in equilibrium calculations is when we are trying to do a shifted initial set of conditions. So, for example, if we have our equilibrium of some sort, and we have 0.01, 0.3, 2.5, 0.6, then it may be a good idea to, depending on what our equilibrium constant is for this, if our equilibrium constant is really small, then that means it's very reactant favored. Then when we make our shifted initial conditions, we are taking this down to zero as if we are doing a limiting reagent problem in reverse. So let's put some stoichiometry in here. So 2A plus B yields 2C plus D, okay? So if we are doing the shift, we recognize we're gonna run out of the 0.01 first, the 2C first. So that means that the X we shift it by initially is going to be half of the 0.01, which is going to be 0.005. So this is going to become 0.295. This becomes 0. This is going to go up by 0.005, so 2.505. This is going to go up by 0.01, so 0.61. And so we have treated this as a limiting reagent problem to set up our shifted initial conditions. But that's just to try to make the math easier. That is not in any sense saying that this actually happens. It gives us an easier way to do the math so that when we get down to the equilibrium line down here, the algebra we have to do is easier. And this is not going to stay at 0 because it is going to be in equilibrium. That general idea there makes some sense? Okay. Okay. Some buffers. So what exactly is a buffer system and which species can form a buffer system? The general idea is that you need to have a reversible acid-base reaction, and the components that make it up are the acid and its conjugate base. So if we have HA plus H2O, it's in equilibrium with A minus plus H3O plus. This is the acid. This is the conjugate base. Think of them as the same thing, just with or without its proton on it. So that's how you know that they are an acid-base conjugate pair, is that they're the same thing, just with or without the H plus. And those are the components that you use to make your buffer. You put in roughly equal amounts of these two components separately. So the acid you can put in directly. The base, the conjugate base, you have to put in as a salt. So if, for example, we are looking at acetic acid, so CH3COOH, its conjugate base is the acetate ion, CH3COO minus. How did I determine what the conjugate base was? Took away hydrogen, that's right. Take away an H plus, and so that's the conjugate base. So this is the acetate ion. And if we want to make our buffer 0.1 molar in this and 0.1 molar in this, then we can do it directly using acetic acid. For the acetate, we put it in as a salt. So we need a positive ion to go along with this. So something like sodium acetate we would put in. So that's how we know which species can form a buffer system. You have to have a reversible acid-base reaction, and then the two components that you put in are conjugates of each other. You can do this as well, starting with a weak base, if you are looking at pHs that are above 7. So you could do a weak base, and then its conjugate acid would be the thing that you're going to combine it with. Okay. Now, the behavior of the buffer system is simply an exaggerated form of Le Chatelier's principle. So the idea is that if we took water and we added some strong acid to it, the pH would change a lot. If we take this buffer system and we add that same amount of acid to it, then we are increasing the H3O plus concentration in this equilibrium, and Le Chatelier says it's going to shift this way and use up some of that H3O plus. How much? Actually, most of it. So resulting in the pH getting slightly more acidic, but really only slightly. We did an example of this on both Monday and Tuesday in class. And in our example, we had the pH shift in a non-buffered system by, I think it was 2.5 pH units. And then in the buffered system, it moved by 0.02 pH units, something like that. So the buffering phenomenon stabilizes the pH dramatically. That's the idea of a buffer. And then we have the question, how do we calculate the pH of a buffer solution using the Henderson-Hasselbalch equation? And I would like to do this, but I would like to first do it using an ICE table so that we can make the comparison about doing it by both different methods. So let's pick a buffer system. Which one shall we do? Let us do, I'm always doing acetic acid. Let me find a different one to do. So, how about hydrogen sulfide? So we have H2S plus H2O in equilibrium with HS minus plus H3O plus. Let me find the pKa for this. pKa of H2S. Wow, the pKa of this is right at 7. That's awfully convenient. Okay, so pKa equals 7. 7.04. So let's set up some initial conditions for this. Let us do an initial concentration of each of these of 0.05 molar. And we will look at what its initial concentration is, initial set of concentrations is at equilibrium using an ICE table. So 0.05, 0.05, do 10 to the minus 7. If we have the equilibrium shift, it's not going to shift by much, but let's say we do minus x, x, and x. So 0.05 minus x, 0.05 plus x, and 10 to the minus 7 plus x. Okay, so x is going to be small compared to these two, but it is probably, and it may be small compared to the 10 to the minus 7, but it's kind of hard to tell at this point, so let's leave it in just to find out. So if the pKa is 7.04, then that means that the Ka is 10 to the minus 7.04. So our Ka, which equals 10 to the minus 7.04, equals our concentration of HS minus times our concentration of the hydronium ion over our concentration of H2S. We plug in our values for this, so 0.05, we're going to neglect the plus x and minus x here, times 10 to the minus 7 plus x over 0.05. Our 0.05s are canceling. Let's see what 10 to the minus 7.04 is. Uh, 0.04, change sign, 10 to the x. So this is 9.12 times 10 to the minus 1, 2, 3, 4, 5, 6, 7, 8 equals 10 to the minus 7 plus x. So we subtract 10 to the minus 7 from both sides. So minus 1, where am I? E7, change sign, equals. And we get that x equals negative 8.8 times 10 to the minus 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, notice that we ended up with a negative value for x. Does that mean we did something wrong? No. All it means is that the assumption we made that the equilibrium is going to shift to the right is incorrect. It's actually shifting to the left. So we now plug our negative x value of x into our expression for the H3O plus here. And so our concentration of the hydronium ion is going to be 10 to the minus 7 minus 8.8 times 10 to the minus 9. So that plus 1 E7 change sign equals, it's going to be 9.12 times 10 to the minus 8. 1, 2, 3, 4, 5, 6, 7, 8, right. And not surprisingly, the value we get here is the same as the Ka that we started with. Our pH is the K, and our pH is going to be the same as the pKa. So, well, the question, this is how you do this kind of problem using an ice table. The Henderson-Hasselbalch equation, I derived it both on Monday and Tuesday, says that the pH of a buffered solution is the pKa of the acid plus the log base 10 of the concentration of A minus over HA for whatever acid it is you're dealing with. In this case, we started by preparation with the same concentration of the H2S and the HS minus. So this ratio here is 1. What is the log base 10 of 1? The log of 1 by
0
at any base is 0, right. So this is 0, which says that the pH of this solution is going to be equal to the pKa of the acid, which is exactly what we just found. So this is a quick way to go about it. See, there's a question here. Why are we neglecting just those x's? So why were we neglecting these two x's? Because we are making the assumption that the equilibrium is not going to shift very much from its initially prepared state. And we find that that is in fact the case at the bottom here. We find that the value for x that we got is very small compared to the 0.05. We don't neglect it here because 10 to the minus 7 is a lot smaller. And in fact, 10 to the minus 7 and 9 times 10 to the negative 8th are very close to each other. Okay, and where did we get the minus 8? So that's just part of the scientific notation here, is 10 to the minus 8, unless you're talking about this part right here. Okay. This one here. So here we started with this, and I simply subtracted 10 to the minus 7 from both sides, and that was the result of what you get by subtracting 10 to the minus 7 from both sides. Okay, so let's now look at taking the same buffer and measuring the effect on the pH of the buffer by adding some acid or base to it. So let us suppose that we are adding, so I'm going to make myself a new ice table. We have our, let's see, we're going to use the same initial conditions. And let's suppose we have a liter of it, and we are adding to it 1 milliliter of 1 molar hydrochloric acid, which is a strong acid. So if we add 1 milliliter to our initial conditions, to our initial buffer system, 1 liter of it, then this is going to get diluted by a factor of 1,000 as it goes from 1 milliliter to a liter. And so this will be 10 to the minus 3 as our initial concentration of the hydronium ion that we have here. Okay. Now, the way to handle this most effectively is to then pre-shift this initial conditions to get rid of all of the hydronium ion. So if we do that, this is going to go down to 0, 0.04, 49. Am I doing that right? I'm in the right place? Yeah, 0.049, 0.051. Okay. Minus x plus x plus x. We expect x to be small compared to these two, so 0.051, 0.049 x, and our equilibrium constant, 9.12 times 10 to the minus 8, equals 0.049 times x over 0.051. We solve for x, and we get 9.12 times 10 to the negative 8th times 0.051 divided by 0.049, and we get 9.3 times 10 to the minus 8th. 1, 2, 3, 4, 5, 6, 7, 8. And so our pH is 7.03, barely shifted from the 7.04 that we started at. Okay. Now, how do we do this same kind of problem using the Henderson-Hasselbalch equation so that you don't have to do the whole ice table? Well, our Henderson-Hasselbalch equation is this one right here. pH equals pKa plus log base 10 of the HA, or excuse me, A minus over HA. Our pKa we said was 7.04. We have our initial conditions for each of these. So 0.05 molar, 0.05 molar, but we've added a 10 to the minus 3 concentration of the hydronium ion to it. So when you add more acid, then that shifts away from this and towards this. So plus 10 to the minus 3 minus 10 to the minus 3. So what we're doing here is just seeing how does the ratio of acid and its conjugate base change as a result of the perturbation we apply by putting in some strong acid or strong base. And if so this then becomes 0.049 over 0.051. We do 0.049 divided by 0.051. We take the log base 10 of that and we add it to 7.04, and we see that we get 7.02, which is within error, within one sig, within a 0.5% of, or 0.1% almost, of what we got by doing this method here. So the Henderson-Hasselbalch equation is a very, very convenient shortcut that you can use to get the pH of a, you can get a pH of a buffered system when you are operating within the buffered region. So within there being between about 10% and 90% of each, the components being of each other. It operates under the assumption that you have pre-shifted the equilibrium based upon whatever your perturbation was. So you know how much of each of the buffering materials you started with. If you add acid to the system, then you convert some of the conjugate base to acid. If you're adding base to the system, you go the other way. So you'd be subtracting from the denominator, adding to the numerator. And so that's significantly faster than going through the whole ice table approach. Okay, so are you guys feeling relatively comfortable with the Henderson-Hasselbalch stuff at this point? Okay, cool. Okay, so the next questions that came up on Piazza were about salts. So before I go on to that, is there any sort of clarification anybody would like on buffers? Especially given that the small group activity is going to be very focused on buffers. Okay, so let's talk about salts then. So there's a lot of confusion, it sounds, on the combination of strong acid and weak and strong base, strong acid, weak base, weak acid, strong base, weak acid, weak base, and all these combinations. The chapter in the section in the textbook that went over this is a laboriously long list of these instructions, and there are lots of Newton questions about these things. And unfortunately, it gives you this impression that there are these special rules you have to deal with for each of these various situations. And it also, but with the way the Newton questions are asked, it gives you the impression that, for example, if you make a solution, if you make a mixture of a strong acid and a strong base, you will get a neutral solution. This is wrong, because you also need to know what the concentrations are. If you have more acid than you do base, then you'll end up with an acidic solution. You also need to know what the stoichiometry is. If you have H2SO4, the diprotic sulfuric acid, mixed with sodium hydroxide, you would need twice as much of the sodium hydroxide for it to be completely neutralize, because that only produces one hydroxide for each one. So I really feel as though the textbook and the Newton emphasis on these kinds of issues is a little bit misguided. Nonetheless, it is true that you can make salts from acids and bases, And so understanding the general process, I think, is a worthwhile thing to do. It's just that you shouldn't be thinking that there's something special or new that you're having to do based upon whether they're strong or weak. And we'll talk about examples of that as we go through this. So a strong acid is HCl. When it gets into water, you get the hydronium ion and the chloride ion. A strong base is sodium hydroxide. You put that into water and you get the sodium ion and the hydroxide ion. If you mix these two solutions together, then the H3O plus will react with the OH minus to form water, and you are left with a solution of sodium plus and chloride minus. What is sodium chloride? Table salt, right? So if you take a strong acid and a strong base, at least these particular ones, and you mix them in the right ratio so that everything, so that the hydronium and the hydroxide exactly cancel out, then you get salt water. This is the idea of what is happening anytime you mix an acid and a base to make a salt. You can mix acetic acid, which goes into water to form CH3COO minus. Let me try that again. And the hydronium ion. You can mix this weak acid with a weak base, and if you mix these two solutions, you again have H3O plus OH minus, creating 2H2O. And you have a solution left of NH4 plus and CH3COO minus, which is ammonium acetate. That's all that's going on. Creating a salt solution simply means that you have a neutralization reaction that is going on to get rid of the acid and base portions of things, and you are left with ions that of opposite charges that make a salt. So how would you collect this? Well, you might dry it off. Or maybe what you're making is something that is insoluble in water and it would precipitate out. The only difference between strong acids and weak acids, strong bases and weak bases in these cases, is whether or not you're having equilibria going on or not. So in this case where everything is weak, then you're still going to have some of the acetic acid here. You are still going to have some of the ammonia here in the mixture. So all that's really going on is you've got more. You have more stuff that's in there at the same time. So an example Newton question that was related to this is, and they say for some reason using the periodic table, which I don't see where that's coming from at all. But it's asking which of the following is a salt that could be generated by combining a weak acid and a weak base. So the way to think about this kind of question is to take the compound, let's start with the first one, NaCl, and let's split it into its components, Na plus and Cl minus. So if you think about what acids or bases these things would come from, Na plus would have to come from NaOH, because we need a negatively charged thing that's associated with it. The Cl minus would be coming from HCl. So NaCl, if it's made as a salt from an acid and a base, is being made from sodium hydroxide and hydrochloric acid, both of which are strong. So we can look at this and see NaCl is not one of the ones we can use because we are looking for a weak acid and a weak base. And you just go down the line and look at each of these. So Na2SO4, we look at this, well, we have the Na pluses. There are two of them, but let's not worry about that at the moment. SO4 2 minus. Well, the Na plus we just said came from NaOH. SO4 2 minus comes from H2SO4 sulfuric acid. Strong acid, strong base, so it can't be that one either. NH4NO3. NH4 plus NO3 minus. Well, we probably can recognize the NH4 because we've used that example before as coming from NH3 plus H2O, yielding NH4 plus OH minus. This is a weak base. But the NO3 minus has to have come from HNO3, nitric acid, which is a strong acid. So it can't be that one. By process of elimination, it has to be this one. We've already explored here how NH4 plus is the conjugate acid of a weak base. The F minus comes from HF, which is the only halogen acid that is a weak acid. HF is a weak acid. So the only possibility is this. So the way to think about these salts is that each ion that is part of the salt could be the product of either a Bronsted-Lowry acid reaction or a Bronsted-Lowry base reaction. You try to figure out which one that is, and you see, is the thing it came from a weak or a strong acid or base? That's the general approach to these kinds of questions. Any clarifying questions or comments here? Okay, I've made it through the muddiest points that I was able to find on Piazza. I am happy to open up the floor to any other kinds of questions. Oh, I did actually want to show very briefly. If you look up this is not going to be legible, but I'll explain what it is, and you can easily find them by searching online. This is a solubility table. Across the top, we have various positively charged ions. And down the side, we have various negatively charged ions. You can conceivably make a salt in most combinations of the positive ion and the negative ion. And this one right here shows you that some of them are soluble, some of them are insoluble, some are slightly soluble. And from the exam number 1, you probably recognize that what we really want in here is probably the solubility product rather than just this statement that it's soluble or insoluble. To a greater extent, what you're dealing with is an equilibrium, and something will dissolve to an extent. But you still get the idea here. But this kind of chart would be a fantastic way for you to practice looking at acids and bases and finding their conjugates and so on. Because nearly every ion on here is going to be the conjugate base of a weak acid or vice versa, or it will be a metal ion that will form a hydrate in water that could make it acidic. And so if you want to have some practice trying to identify different kinds of acids and different kinds of acid-base reactions and so on, looking at something like this to come up with a variety of combinations would be a great way to go. So you could, for example, say, I'm going to look at the iodide of magnesium, which happens to be soluble. And well, iodide, we know that it comes from hydrogen iodide, which is a strong acid. Magnesium probably comes from magnesium hydroxide, which is, I believe, a strong base. So you can find, at any intersection here, you can find an example that you could work through. And all you would need to do to find this is just do a Google search on ionic compound solubility table or something like that. We have about 10 minutes left. What can I try to clear up for everybody? I will say that we're going to have several more equilibrium-based topics next week that we'll be looking at. One of them is going to be specifically acid-base related, and it's called titrations. And titrations is about following the pH of a sample all the way from acid to base, or vice versa, as you are adding more acid or base to the sample. And so you add 1 milliliter and you make it more acidic. You add one more milliliter, you make it more acidic. But how much does it get more acidic, and so on? And so this is a very powerful tool in analytical chemistry to quantify the nature of solutions. So as a result of it being so powerful, we're going to go into it in some detail next week. But because it is so heavily involved in calculating the pH under different conditions for a system that may or may not be buffered, trying to get yourself comfortable with these calculations this week on Newton in particular is going to be very beneficial to you, because we're just going to be building on that skill next week. All right, well, I am not hearing other questions. So I guess we can call it for today. Everybody have a good weekend, and don't forget the small group activity. Don't forget to check your new groups. Don't forget to, if you care about which day you want the thing to, the assignment to be due, don't forget to vote in the poll on Piazza. Thank you very much.